So in the previous lecture, we saw that having a very specific permutation scheme of letters, while it gives a really complicated looking scheme, it's not always very secure because of the limitations of the English language, right? However, because we are because of how easy it is to construct such a scheme, and in general, um, without relying on the probabilistic techniques, it is really hard to deconstruct such a scheme. And so we are going to look at how to make such a scheme, affine, what is it called? Affine cipher. So we are going to first look at affine ciphers before moving on to more complicated cipher. So this is a relatively easy cipher, and we will be again using number theory. So using modulo arithmetic. Okay, so we we defined what x mod what x what it means by x mod y, sorry, x congruent to y mod n, x congruent to y mod n if and only if x n divides x minus y, right? This was my definition of writing x is equal to my y mod n, and we discussed some properties that first, if x is congruent to y mod n and a congruent to b mod n, then let me do this. If then first x plus a congruent to y plus b mod n, second x minus a is congruent to y minus b mod n, really easy, and third x times a is congruent to y times b mod n. This is a stronger statement than what I had written last time, okay? And this is true. However, note, division does not work. For example, 28 is congruent to 2 mod 26, right? But obviously 14 is not congruent to 1 mod 26. So unlike addition, multiplication, and division, addition, multiplication, and subtraction, division does not work for these. Okay, so let me introduce some notation before notation. By Zn, we will be writing the set 0, 1, dot, 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 all the way up to n minus 1. And so in particular, we will be concerned with we will be concerned concerned with Z26, which is 0, 1, dot, 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 25, as this allows us to give a to associate a number to each letter, right? With a is equal to 0, b is equal to 1, c is equal to 2, so on, with z is equal to 25. Okay, so now this way we saw how to create the shift cipher, which was exactly moving everything by one fixed amount. But um, we want to know how you can use it to create a more general cipher. So affine ciphers, affine ciphers are ciphers of the form ENC, encryption of x, encryption with k of x is equal to ax plus b mod 26. Okay, so now I am going to take a letter x and I'm going to send it to my to another letter ax plus b. So in this case, my key space, in this case, my message space is going to be message space is equal to just z26. I'm going to look at what happens to each individual letter, map it, and then construct the whole message by just encrypting each letter. Okay, so now the question is, question, do any A and B work? Question mark. So what does it mean by can any A and any B work? Well, what we want is i.e., that is, can it happen that ax plus b is congruent to ax prime plus b mod n? Because in that case, both of them will be encrypted to the same thing, and then I don't know if I can safely decrypt them back, right? Because in this case, we definitely wouldn't be able to decrypt them back. And the question, and this means, therefore, if I move things around, ax minus ax prime is equal to b minus b prime. Sorry, this should be this is congruent to b minus b mod n, which is to say a times x minus x prime is congruent to 0 mod n. Can this happen? And the answer is yes. Yes. For example, if I take a is equal to 2, n is equal to 26, then I can have that 14 times 2 plus 0 is congruent to 1, and 2 times 1 plus 0 mod 26, right? And so this is not great. I have to be slightly careful. Okay, so when does such a thing work? Another example where things won't work is, this should be for example, so for example, a is equal to 2, n is equal to 26, or another example, a is equal to 13, n is equal to 26, in which case, let's say 13 times 4 is congruent to 13 times 6 mod 26, right? Because both of them are exactly 26, which is congruent to 0. Okay, and so in both these cases it fails. The question is, when does it exactly fail? And so the idea is, when is the mapping x goes to ax plus b 1 1, right? A 1-to-1 map. 1 1 2 1. And the answer is, well, plus b definitely always shifts and is 1-to-1. Plus b is always 1-to-1. So that everything relies on a, and therefore the map is 1-to-1 only if a is one of the following. So it can be 1, a is equal to 1, 3, 5, 7, 9, 11, not 13, 15, 17, 19, 21, 23, 25. And what is special? i.e., all of these numbers have the property that GCD of a and 26 is equal to 1. Okay? So these numbers we are going to denote by something special. We denote it by Zn, all numbers from Z1 from 0 to n minus 1. I'm going to say, let me do this. Definition: let Zn star denote the set of all numbers smaller than n that are coprime to n. So therefore, in other words, Zn star is defined to be the set of all x greater than 0, well, x in Zn, such that GCD of x comma n is equal to 1. Okay? And now the question becomes, can I prove that this is 1-to-1? Theorem: the mapping x goes to ax is 1-to-1 if and only if a is in Zn star. Okay, so I am not even claiming this for just for 26. We are claiming it for any n. Okay, here's the proof. So if and only if means I'm going to prove this way and the other way. So let us first assume that the mapping is 1-to-1. Okay, if the mapping is 1-to-1, then if mapping is 1-to-1, then there exists some x in Zn star in Zn such that ax is congruent to 1 mod n. Well, 1 mod n, which is to say therefore n divides ax minus 1, and therefore that means there exists some k in n such that k times n let me such that ax minus 1 is equal to k times n, and therefore ax minus kn is equal to 1, right? Well, this means if if a and n had, if p divides a and p divides n, then p divides ax minus kn, right? Therefore, but ax minus kn is exactly 1, therefore a and n are coprime. Okay. For the other way around, we are going to assume we want to show that if a is in if a is in Z star, I want to show that the mapping is 1 to 1. What if we are going to do is actually show the contrapositive? We are going to say, suppose the map is not 1 to 1. Suppose the map is not 1 to 1. Okay? So if the map is not 1 to 1, there are going to be two numbers, then there exists x comma x prime in Zn such that ax is congruent to ax prime mod n, right? Therefore, a times ax minus ax prime is congruent to 0 mod n, which is to say, therefore, ax minus x prime is equal to k times n for some n, for some k. Great. Well, let us expand out. Therefore, a times x minus x prime is equal to k times p1 times p2 times dot 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 pn, p maybe m, pm, where n is equal to p1 p2 dot 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 pm is the prime factorization, right? But now we have that x minus x prime belongs to Zn, right? And so is between 1 and n minus 1, right? So at least one of the n, so at least one of the PIs must divide A, because if none of them divide, then their product does not divide. Well, their product, sorry, if all of them divide, then their product should also divide, but their product is exactly n, and x minus x prime is bigger than n, smaller than n, right? Therefore, GCD of a comma n is not equal to 1. Okay, and so in both of these cases we get that so we have shown that the map is 1-to-1 only if a is in Zn star. Okay, so now how do we use this? Well, okay, so the encryption algorithm now for me is encryption of encryption of x is equal to, let me use ax plus b mod 26, where a belongs to Z26 star. But question then becomes question, how do I decrypt? How do I decrypt the message? And what you should note is that we know that our transformation ax plus b is a linear transformation, right? And so its inverse image is also going to be linear. Therefore, decryption k of c must also be a linear transformation of the form a prime x plus b prime, or a prime c plus b prime. Okay, so what do we want? Want decryption k of encryption k of x to be equal to x, which is to say a prime of ax plus b prime is equal to x. Therefore, mod 26. Mod 26 congruent to x mod 26. And so I get a prime x plus a prime b plus b prime is congruent to x mod 26. And therefore, a prime x minus x is congruent to minus b prime minus a prime b mod 26, right? Which is to say a prime minus 1 times x is congruent to minus b prime minus a prime b mod 26. Now note, left hand side has x, right hand side does not. This should not depend on x, right? Therefore, this should not depend on x. Therefore, what this means is that a prime minus 1 is going to 0 mod 26, and minus b prime minus a prime b is going to 0 mod 26, right? That's the only time multiplying by x for whatever x is going to keep things the same. Therefore, I get a times a prime is congruent to 1 mod 26, and let me write this down. Minus a prime b is congruent to B prime mod 26. So now the question becomes, how do I solve for A times A prime is equal to 1? How do I even find what A prime is? Question: how to find A prime such that A times A prime is congruent to 1 mod 26, or let me just say 1 mod n. Notation, let me just say A inverse mod n is equal to the unique x in Zn such that Ax is congruent to 1 mod n. Okay, so basically we are asking, therefore, question how to find A inverse. Okay, and the idea is we would like to use wait, I didn't complete the previous one, but okay. How do we find A inverse? We use Euclid's algorithm. Euclid's algorithm. So Euclid's algorithm says if A, G, C, D okay, if GCD of A and N is equal to 1, then we can find x comma y such that Ax plus Bn is equal to 1. Okay, how do we find this algorithm? RTHM. How do we find the algorithm? Let GCD of so in the first step, okay, I seem to be forgetting the algorithm, but for now, let's forget about the algorithm. The idea is that the Euclid's algorithm does tell us that we can find Ax and By. Then A inverse is just equal to x mod n. Okay, and then my solution for B prime, then B prime is equal to negative A inverse times B mod n from here, mod 26. I guess I don't need mod n. Mod 26, And therefore the decryption algorithm, decryption of C, is simply going to be A inverse of C minus B. Okay, and that allows us to use our affine cipher to encrypt a message, and we have the decryption. Check. I'll just say check decryption of encryption Q of X is equal to X. Okay. And so I'll stop this one here. Next time we'll look at more complicated ciphers, starting with probably Vigneri ciphers.